All right, let's dive in. Today we're going to get into the foundations of mathematical certainty itself. We're talking about discrete mathematics, and step by step, we are going to build our way to an answer to one of the most mind-bending questions you can ask.
And here it is. This is our big question. I mean, it seems a little absurd, doesn't it? Infinity is, well, it's infinity. How can one be bigger than another one? So how do we even start to tackle a question like this? Well, you're about to see that to answer something this huge, we have to start with some very, very small and precise tools.
Exactly. Before you can build a skyscraper, an idea like different-sized infinities, you have to lay the foundation, right? We have to agree on the language we're using and the rules for how we build with it.
And that language is logic. You can think of this as the alphabet of truth. It's the system we use to create statements that are completely, totally unambiguous. And in math, that is absolutely essential. Okay, so the smallest possible building block, the atom of our language, is called a proposition. All it is a simple statement that has to be either true or false. There's no gray area, no kinda. The sky is blue is a proposition. In mathematics, you can only build with blocks that are solid, either true or false. No paradoxes here.
So, now we can start connecting these propositions. And the most important connection for us is the implication. You know it as the if-then statement. We write it as P arrow Q. This little arrow is the bedrock of pretty much every mathematical theorem ever. If this one thing is true, it guarantees that this other thing is also true.
Here's a super simple example. Think of it like a machine with one rule. If you put in a number that you promise is a multiple of 4, then the machine promises, it guarantees, that the number that comes out will be even. The first part being true forces the second part to be true.
Now this table right here, this is how logicians define this relationship. The first two rows make total sense. If you start with a true premise and get a true conclusion, the logic holds. True. If you start true and get a false conclusion, the logic is broken. False. But check out the bottom two rows. If our starting premise P is false, the whole if-then statement is considered true. Why? Well, think about our rule. If I start with the number 7, which is not a multiple of 4, have I broken the rule? Nope. The rule just doesn't apply. This little detail is actually the secret key to a ton of mathematical proofs.
So, we've got our alphabet. Now we need the blueprints. How do we put these logical statements together to build an argument that is completely unshakable? Well, that's where the rules of proof come in. There are two main strategies here. The direct proof is what you'd expect. You start with P, and you just march forward with logic until you get to Q. Simple. But sometimes that's really hard to do. The scenic route, or proof by contrapositive, is often way more clever. Instead of proving if P then Q, you prove something that is logically the exact same thing. If Q is not true, then P must not be true. It's a powerful and sometimes kind of sneaky tool to have.
Okay, we have our language of logic. We have our blueprints for proof. We are finally ready. It's time to go back to our big, crazy question and construct our masterpiece. So, to talk about the size of infinity, we need a better word than size. Mathematicians use the term cardinality, and the rule's actually pretty simple. Two sets have the same cardinality if you can pair up every single element from the first set with exactly one element from the second set, with absolutely no leftovers. It's called a one-to-one correspondence. And this is where our intuition about infinity just completely breaks down. It turns out you can pair up all the integers and even all the fractions with the counting numbers. These sets are called countably infinite. But the mathematician George Cantor discovered something that shocked the math world. You cannot do this with the real numbers, all the decimals on the number line. There are just too many of them. He called these uncountably infinite. Cantor proved this with a truly mind-blowing theorem. It basically says you can always create a bigger infinity. It's like if you have a set of people, the number of possible teams you can form from those people is always bigger than the number of people you started with. His theorem says this is true for any set, no matter how big, even an infinite one. So how did he do it? With one of the most brilliant and elegant ideas in all of mathematics, the diagonal argument. It's a proof by contradiction. So step 1, you assume the opposite of what you want to prove. Let's assume we can make a complete list of every single real number. Now for step 2, we're going to build a new number that, I promise you, is not on that list. Here's how. We go down the diagonal. We look at the first digit of the first number on our list and we just change it. That's the first digit of our new number. Then we go to the second digit of the second number and we change that. That's our second digit. We just keep doing this forever. What have we done? We've created a brand new number that we know for a fact can't be on our complete list. Why? Because it's different from the first number in the first position, different from the second number in the second position, and so on. It's different from every single number on the list. We found a contradiction, a number that has to be on the list, but isn't.
So what does that mean? It means our initial assumption, the one that said we could make a complete list in the first place, had to be wrong. And there it is, proven with absolute logical certainty. Some infinities are, in fact, bigger than others.
Now, this powerful toolkit isn't just for playing around with mind-bending ideas about infinity. It's actually used to build entire fields of mathematics that literally power our modern world. For example, take combinatorics, which is just a fancy name for the science of counting things. Using these same formal rules, we can figure out exact formulas for things like permutations, where the order you pick things in matters, like who gets gold, silver, and bronze, and combinations, where the order doesn't matter, like just picking 3 people for a committee.
Or what about graph theory, the study of networks? It looks so simple, right? It's just dots and lines. But this provides the mathematical structure to analyze everything from your social network to internet traffic to flight paths for airlines and even molecular biology.
So, okay, why does any of this abstract logic and these weird infinities, why does it really matter? Because this way of thinking, this demand for rigor and structure, well, it's the secret engine of our modern world. Seriously, every single time you use a computer, you are using the principles of discrete mathematics. The algorithms that make software run, the cryptography that keeps your information secure, the way data is stored in databases and sent over networks, it is all built on this foundation of logic, sets, and graphs. It's the invisible architecture of the 21st century. Think about it. We've used these tools to prove that infinities come in different sizes, and we used those same tools to build a digital world that was completely unimaginable just a century ago. So it really makes you wonder, with these fundamental building blocks of certainty, what new structures, what new realities are we going to build next?